So Wendy Freedman from the University of Chicago will be telling us about the new results from JWST related to Hubble Tension. Wendy, so you know, we are in a very nice lecture room. There are about 150 people watching your talk. Yes, please take it away.
Well, thank you very much for the opportunity to speak. Thanks to the organizers for inviting me to do so. I'm sorry I can't be with you in Krakow. I'm speaking to you now. It's morning here in Pasadena, where I am today. And I'm going to present some new results from JWST. I think as this audience needs no introduction, JWST provides an important new tool to address the accuracy of the local distance scale. And we've seen in the last few decades, first with the launch of HST and ability to get above the Earth's atmosphere and at that time improve the resolution of measurements of Cepheid variables by an order of magnitude, not having to worry about turbulence in the Earth's atmosphere. And the Hubble Space Telescope has been a workhorse in terms of finding Cepheids in nearby galaxies and its optical capability, where Cepheids, of course, have larger amplitudes in the optical than in the infrared. And so discovery of Cepheids has really been a strength of Hubble and allowed us originally to resolve the tension at that point, the debate of a Hubble constant with a value of 50 versus 100. And of course, with the Planck results and measurements earlier from WMAP, as the fluctuations in the microwave background measurements improve, the ability to estimate the Hubble constant in a completely independent way, which are giving a lower value of the Hubble constant than is being measured locally. So this tension that we've seen is a Hubble and Planck discrepancy. And JWST, of course, offers much greater resolution and sensitivity out into the infrared, and that's where many of the systematics that have plagued the distance scale for decades, in fact, JWST offers enormous potential for overcoming systematics that might be remaining in the distance scale. So I think at this point, JWST really is just beginning in terms of what it can do. I don't think we have a resolution to the tension. I'm not going to state that we do have a resolution at this point, but I think the potential for overcoming systematics and reducing our systematic uncertainties is phenomenal because of JWST. So we seem to be able to advance in the same way. Let me see, this works. Okay. Now what I'm showing here is the measurement of the Hubble constant as a function of the year of publication of the results, and beginning here just slightly before the key project, we measured a value of 72 with an uncertainty of 10%. And the values that I'm showing here in red are all Cepheid-based calibrations. Most of them have been undertaken by the SHOES group since the time of the key project. This Carnegie Hubble project measurements was based on Spitzer Space Telescope observations in the mid-infrared and was a recalibration of the earlier key project data. You see that the Cepheid values, and I should say that these are tied in to type 1a supernovae. The Cepheids, of course, don't go far enough out that you can overcome uncertainties due to peculiar flows and peculiar velocities. So the value of the Hubble constant has stayed pretty much constant since the time of the key project, but what really has changed are the uncertainties, and the uncertainties now estimated to be at the 1% or so level. And they are indicating that there may be a discrepancy with the Planck measurements, which are giving a value more like 67. So you'll notice that the Cepheid measurements do tend to be rather high compared to the other published values, whether that is significant or not, whether they really are indicating the true value of the Hubble constant, I think we have yet to ascertain, and that's what will come in the next couple of years, I believe. So we can ask, what are the challenges in measuring an accurate local value of the Hubble constant? And clearly, the Planck measurements have set an entirely new bar when we come to measurements of the Hubble constant. They are measuring a value of 67.4 with an uncertainty of only 0.5 kilometers per second per megaparsec, and that's a precision of better than 1%. The certainty are not there in terms of the extragalactic distance scale, where we have to be concerned with issues of first calibration with geometric techniques locally. Then as we move out to the realm where Hubble, or now JWST, can measure Cepheids or tip of the red giant branch, or JGB stars, carbon stars, as I'll talk about in a moment, and then step out to type 1a supernovae, where you get beyond the issue of peculiar motions. And so each one of those steps provides a challenge. And if we're going to measure a value of the Hubble constant overall to an accuracy better than 1% or 1% or so, to be certain that we are comparing with the Planck measurements at a level that is comparable, that is a very, very tall order. So the measurements of the Cepheids with HST, of course, the supernovae are very rare. If they go off once per century or so in a galaxy, then building up a sample of nearby objects that have also hosted type 1a supernovae takes a long time. There are about 42 supernovae now in 37 galaxies that have been heroically measured by the SHOES team. But, and as I mentioned, HST is optimized for the optical. When we look in the near infrared, this is an example of a Cepheid in NGC 7250 at a distance of 20 megaparsecs. Now, and the red circle here indicates the position of a Cepheid that was discovered in the optical and then followed in the infrared. Now, it's difficult to choose an appropriate scale here, the stretch in which to show these measurements. This is another example that Adam is showing for the comparison in NGC 7250. And you can certainly see that there is flux in this measurement, but if we compare now with JWST, which is to take nothing away from HST, HST was the whole discovery machine, but following up in the JWST in the near infrared, you can see that the resolution improves enormously. Here's another example. And this is now using a pixel scale that I hope Adam will agree that is more comparable to JWST. So you can see there is flux at the position of the Cepheid, but there are a lot of nearby objects that are brighter. And the signal to noise in the HST data compared to JWST in this case is almost an order of magnitude in some cases. So in terms of measurements, JWST is offering, here we go, this is the Cepheid now with JWST, improved resolution and improved sensitivity. So we can do much better at this point. Now, the results that we have to date, I just want to point out, we've used 3 different methods: the tip of the red giant branch, these carbon stars or JAGB stars, a class of carbon stars, and the Cepheid PL color metallicity relation. And our results for the tip of the red giant branch and JGB stars are based on JWST data alone. We can't do that yet for the Cepheids. We have to still rely on HST data to get colors and therefore be able to correct for reddening. Now that will change, of course, as more JWST data become available, but at the moment there aren't enough observations with JWST to be able to do it with JWST alone. That will come in the future. So well to keep in mind that at the moment we have JWST results for TRGB and JGB alone, JWST, but not yet for Hubble and Cepheids. Okay, so I don't think I really need to dwell on this for this audience, but just in terms of overall characteristics, JWST, of course, is a 6.5 meter telescope. It's much larger than Hubble, and it's optimized for the infrared. It has gold-coated beryllium mirrors, and it's located at the L2 orbit, 1.5 million kilometers away from Earth, as opposed to HST, which is in an Earth orbit. And it has almost 10 times the sensitivity of HST is at near infrared wavelengths, which the wavelengths we're observing, and more than 3 times the resolution with the cameras that we have used. And our program is to measure distances using these 3 independent techniques. So that does not rely on a single technique, but as we're measuring distances to galaxies, the opportunity now to compare within a single galaxy, different types of measurements, I think is extremely important, because each type of method is going to have its own internal systematics, some of which at the current time are likely unknown. And determining overall what the systematic uncertainties are will require more than one method. If we use only one method, we may be left with systematics that we just don't yet understand. So any differences that we have within the galaxy based on these different methods are not giving an indication of a discrepancy with the early universe. They're giving a discrepancy amongst the distance indicators themselves. And that's really important to ascertain the level of before we can look for differences in the early universe. We carried out the analysis of the photometry completely blind. So the first stage of our analysis was done with adding random numbers to our photometric catalogs, essentially throwing away the key, and in different parts of our group did the analysis separately without any knowledge of what was being done by the other parts of the group. And then we got together and compared those results. And at that point, we were completely blind. At this point, it's interesting, as I'll show you, there are other, particularly with the Cepheids, areas where we tried again to remain as completely blind as we could by having different subsets of our group analyze the data in different ways. But there are choices to be made having to do with, for example, cuts at which you determine period cuts in the period luminosity relation, how you correct for reddening, and what you do with outliers, et cetera. And so interestingly there, when we did that kind of blind analysis, we came up with different results. So the results aren't completely blinded in the sense that when the day that we unblinded, nothing else was ever considered again. But there are complexities that make this kind of completely blind analysis difficult for the local distance scale. But we aimed as much as possible to do this analysis separately and not be affected by any other analysis that had been done previously. And in terms of the photometry, that was all done blind, and the initial results were all blind. They haven't changed by, outside of the error bars, but it's not, I would say, a completely blind analysis at this point. To the extent that we could, we have independent groups looking at the different ways of analyzing the data, and then we only compare it at that point. Here are our fields. So we observed 11 galaxies in total, including our calibrating galaxy, NGC 4258. NGC 4258 is the galaxy containing these water megamasers and has a geometric distance, measuring the rotation of the masers in this edge-on Keplerian disk, and offers this potential to get a geometric distance for a galaxy in which we can do all of the measurements with JWST. So we have no worries about transforming to the ground. NGC 4258 also has a metallicity, which is comparable to the average of the rest of the sample. And so the metallicity corrections are small, and that's a help, particularly with the Cepheid analysis. So we've aimed to do all three measurements simultaneously for the Cepheids, JAGB, and TRGB. And so here in the red are shown the positions of the near-infrared camera. And we've aimed to have one of them as far out in the halo. You can see in some cases we've been more successful in that. But the point is, we don't want to be doing the TRGB or the JAGB observations right in the disk. The advantage of the tip of the red giant branch is that you can make measurements far away from the disk where you have more dust, where the crowding and blending issues are larger, and so you don't have these extra complications that you do with Cepheids. And with Cepheids, we're confined to the disk because they're young stars, and that's where they're located. They haven't yet had time to diffuse away from the regions where they were first formed. And there's no point in measuring the TRGB closer into the galaxy, because then you inherit these extra complications that you have to deal with the Cepheids, and you don't with the tip of the red giant branch if you can move far out into the halo. So that is an advantage of that method. Each method, I would say, has its own advantages and disadvantages, and that's, again, why you'd like to make these measurements in more than one way. So we've done this to try to get the pointing of the telescope so that we could analyze all three types of measurements with our JWST first observations. And here is a galaxy NGC 4536 and one of our target galaxies. We've observed in the infrared now where there is actually a slope to the position of the giant branch. That can be rectified in the sense that you remove that slope and you can still measure an edge very accurately, as I'll show you. And here's the position of these JGB stars. Most people probably aren't yet familiar with this method. I'll describe that in more detail in a moment. And then the Cepheids, which are the brightest of the three distance indicators, and this is where they lie in the color magnitude diagram in the instability strip. And the advantage is that we now have these independent techniques. They are, in terms of underlying physics, completely different physics involved in each of the methods. I should have said the TRGB we understand very well theoretically. That is, it can be predicted what the bolometric luminosity will be of these stars from first principles. We can't yet do that for JGB or Cepheids. They're located in different environments, as I've alluded to, so they have different effects of crowding or blending and dust and chemistry. And they're very different evolutionary stages and masses. So again, the potential systematics of each of the methods are going to be very, very different. We have the advantage of using the same detectors now, same filters, same point spread functions, same software analysis. I should say we use different software and compare to get a better handle on the uncertainties in the photometry, and the same absolute calibration. So we're comparing on the same scale. Now, the tip of the red giant branch, these stars, the giant branch stars, are at a phase of evolution where they have a degenerate helium core that's surrounded by a hydrogen burning shell. And so the hydrogen burning shell is depositing more helium onto the core. And when the temperature reaches about 100 million degrees, it's well understood in terms of models, which have been for decades now well understood. You end up with a temperature high enough to ignite the triple alpha process. And then you get a thermal runaway because the core is degenerate. You lift the degeneracy, and the star then falls onto the horizontal branch, and then is no longer climbing the red giant branch. So observationally, it's a very nice and very simple in principle measurement. And I should point out, so here's the giant branch. There are also stars that are more massive that are part of the asymptotic giant branch. These AGB stars are not as numerous as the red giant branch stars, so they add a pedestal to the luminosity function. So the luminosity function is shown here in gray. But the position of the core helium flash can be measured really quite accurately. So we look for the first derivative in the luminosity function. We've used edge detection techniques that are well understood from image processing. For example, these Sobel kernels. And when you have high signal to noise data, it really doesn't matter which kernel you are using or if you use a maximum likelihood technique, and we've experimented with both. So here again is the red giant branch here, and here are the asymptotic giant branch stars, which provide a pedestal again. But if you look at the luminosity function, this well-defined edge is quite clear. And there have been some debates about what type of method is better to use. When you have accurate data, it really doesn't matter what you use, but I just want to make the point that in terms of fitting a slope to the red giant branch or the asymptotic giant branch, which you do in a maximum likelihood analysis, if we think of the analogy of a cliff, you can determine this slope really well, but as you come to the edge, this part of the slope knows nothing about the edge. Similarly, neither does this part. It's really the edge that you're trying to measure. So knowledge of the slope here and adding extra parameters really doesn't help you in terms of defining the edge. So again, when you have high signal to noise data and enough stars to define the tip, then an edge detection technique measuring the first derivative of the luminosity function is really what is telling you where this edge is. So here's an example of our data, some of our data for JWST. And we tried to optimize so that we could observe at a range of distances here from 7 to 15 to 22 megaparsecs. We limited in our first cycle observations our data to distances less than about 23 megaparsecs. And the point was to make sure that we weren't having issues with crowding and blending. So the nearest galaxies in the sample that were likely to be least affected by crowding blending effects. And you can see the signal to noise levels here are quite good in all cases. So we're not looking at signal to noise of a few. And many stars that do define the position of the tip. And just here are some other examples now for the rest of the sample. And you can see, even by eye without quantitative measurement, that the tip is quite well defined, and that measuring in the infrared with the slope, you can still very accurately determine the position of the tip. So the second method we've used is the JGB method. And this is a method that's quite new in terms of its application to the extragalactic distance scale. It was originally found by Nikolaev and Weinberg, studying stars in the Large Magellanic Cloud. And these are stars that are, in this case, have a degenerate carbon-oxygen core. They're more massive than these red giant branch stars, and they're double shell burning. They have both hydrogen and helium burning shells. And the reason that they work as a distance indicator is that, and empirically, they have a very small intrinsic dispersion in the near infrared. It's about 0.2 magnitude, as found by Nikolaev and Weinberg. And the reason physically is that the higher mass stars, so in the carbon stars, stars are being, carbon is being dredged up to the surface at this phase of their stellar evolution. And for the most massive stars, the temperature is high enough that it's actually burning the carbon before it can get to the surface. For the lower mass stars, the dredge up is never occurring. It doesn't go deep enough into the interior to dredge up the carbon to the surface. And so empirically, you end up here's the J band at about 1.2 microns. These are original observations by Nikolaev and Weinberg, which showed, their analysis was in the LMC, this is not their analysis, but showed that this dispersion in the luminosity of these carbon stars at J is really quite low. And they actually did this at K, where there's a bit of a slope. We then realized that at J, the magnitude of these stars is quite constant. And what they were able to show was that the LMC has a geometric tilt, and that had been seen before with Cepheids and other indicators in the LMC. And a spectacular demonstration that even though one might imagine there could be systematic effects, perhaps due to differences in star formation and so on, they can't be large enough or that would dominate the signal, and no measure of the geometric tilt would be possible. So Barry Mador and I used data that had been published for galaxies that had been observed with ground-based telescopes, and measured the position of these carbon stars, the luminosity function, and derived distances and compared those with published distances for the tip of the red giant branch. And that's shown here. And these were not data that were optimized for measuring these stars. But a first look indicated that this was a promising distance indicator. And so we went on to, we applied first the technique to archival data from HST. And again, that looked very promising. And so we applied for cycle 1 JWST time to do the three methods as I've shown you. So here are our first measurements using JAGB stars. And here are the regions beyond the white ellipses and other markings shown here, where we made these measurements. And you can see the luminosity functions that have been measured in all of these cases, fairly symmetrical. We use the mode, and that gives us a distance indicator for these galaxies using this method. And finally, of course, the last method is the Cepheid distance scale, which really has been the gold standard in terms of extragalactic distances in measurement of the Hubble constant. And we've known for a long time that the amplitudes of Cepheids decrease as you go to increasing wavelength. So again, observing with Hubble, say with the VNI filters, which is what we did for the key project, the shortest wavelength band has the largest amplitude, which allows you to discover the Cepheids in the first place, and follow up with the longest wavelength that you can, allows you to get leverage on the reddening. The scatter in the PL relations also decreases as a function of increasing wavelength. These are data again from I should say these were Milky Way data here. This is data from the Large Magellanic Cloud, and you can see very small dispersion in the PL relation. And with multiple wavelengths, this line here is a fit to a galactic extinction law, and you can see that you can correct well, even observing with optical bands with HST, using a galactic extinction law. Whether you use W, the Wessenheit function, that's simply making use of VNI, that part of the extinction curve. But in both cases, you're using the same ratio of total to selective absorption. How you do that is somewhat dependent. It's dependent on how many wavelengths you have and which method you prefer. But you need several filters in order to be able to correct for reddening. And that's why we are still using HST data. At the moment, we don't have enough infrared data to do this. So why is 1% so hard? And I'm going to just make a slight digression here. I just want to just quickly run through our analysis. We had to redo everything because the pipeline changed for reduction of our Dolpho data. We've reanalyzed everything from the archive from scratch. That is, we're not going from published data, but we're doing our own analysis of the HST data. We haven't included the H-band data. Rather, we've taken the JWST J-band data. We've done an enormous number of artificial star experiments, 1,000 stars for each Cepheid, injecting them, very few or one at a time, and then reanalyzing those in the same way as we do the actual data. So we've corrected for extinction using all three wavelengths. We've used both Dolpho and DAO to check internally that our photometry is robust. And compared with aperture photometry from ST, as I mentioned, all of the initial analysis was done completely blind. And we've looked at supernova samples, and the calibration is based on NGC 4258. So I just want to say a few words about the improvement in the near infrared and why you want to go to the infrared. These are data that we obtained with Spitzer over a decade ago. This is ground-based data, JHK, taken at Las Campanas, and here are Spitzer data at 3.6 and 4.5 microns. What I want to point out is if you look at the individual Cepheids in the PL relation and the scatter about the mean fit, the residuals correlate extremely well. These are data taken with completely different telescopes, completely different analysis, et cetera, et cetera. But when you have high precision data, you can really measure very accurate distances using Cepheid variables. So these are still precision tools, but you do need accurate data. So we had light curves at each of these wavelengths. They're very well sampled. This is an example of our Spitzer light curves. There are error bars shown here. They're just smaller than the data points themselves at 3.6 and 4.5 microns. So this was Milky Way. Here is the Large Magellanic Cloud. But as the distances increase, so now as we go out in distance, and you still need the optical data from HST to do the extinction corrections, the precision and accuracy obviously decrease. So here are PL relations. This is, again, archival data, F555W and 814. And here are J-band data. This is NGC 5643. Here is 4639. And the data weren't taken. They're not phased. So there's no correlation of the residuals that you can see here. So we're not dealing with the same kind of precision that is in principle possible for Cepheids, but not present in the current data. And so we need accurate colors. The colors are important for determining reddenings. You need to be able to correct for metallicity. You need to have crowding corrections for your stars, and these effects are degenerate. So if you have errors in these colors, you're going to have errors in your distances, and these effects, as I said, are quite degenerate. So this is a comparison now of, here's a B minus V color compared with V minus I for a Cepheid in the Large Magellanic Cloud. The colors are reflecting temperature, so this is a real effect, and they have to correlate because this is one star, and the colors are very accurately determined. If we look at the colors for the galaxies that have been had Cepheids discovered with HST and now follow up with JWST. So these are data from Rees et al. 2024. This is NGC 4258, so fairly well-defined slope here, although the scatter, of course, is larger. These are galaxies that are more distant. So this is a galaxy at 7.6 megaparsecs. But if you go to 20 megaparsecs now, you can see the scatter really does blow up. So if in this color plot, the slope is reasonably well defined by 4258. The scatter in V minus I color is very large, and it amounts to about 12% in accuracy. So here it is, the same scatter compared to the LMC. We're working with colors that at the moment, there's still uncertainty. Okay, I'm not going to spend a lot of time on metallicity. This is something that is, of course, you need to correct for Cepheids. There's a range of values in the literature. People are still debating what that actual value is. There's a range that goes between about 0 and minus 0.5, and even recent Gaia results, people who are analyzing these data get very different measurements of this slope gamma for metallicity. So the general tendency is to take gamma about minus 0.2. We've applied that, but again, there's uncertainty involved with that. There's uncertainty in the artificial star corrections. They're very small at J, but they are significant at V and I. And again, this couples into how well can you correct for extinction, for metallicity, for crowding, blending, and so on. So let me say a few words about the distances that we're getting for the tip of the red giant branch and JAGB. So here's a JAGB modulus compared to tip of the red giant branch. You can see the comparison is an excellent comparison. And the scatter is less than a couple percent in distance, and the offset is almost negligible. So you saw on the color magnitude diagram, those two methods are, they should correlate well. We're measuring each of the distances within a galaxy. If the methods work, then that offset is going to show good agreement. It's harder with the Cepheids because they're just more complex. You need periods, you need to correct for more reddening, you need to correct for metallicity, et cetera. So the agreement with the Cepheids is not as good. There's an offset of these two with respect to Cepheids, which ultimately we're going to have to understand. There's a simplicity here in these two measurements, and the next level, of course, is taking those and applying them to the supernova distance scale, and that, again, is another level of where discrepancy can arise. I am just showing here the comparison. These are published data, again, from the ground for JGB and TRGB, but you can see that all the way out, the calibration is quite consistent, and this is showing a very steady calibration of both of these methods. Just quickly, I just want to emphasize that this is from Rees et al. 2022 that shows the progression out from the geometric distance indicators to the Cepheid realm with HST at this point, and now JWST, and then into supernovae. And so our difference here, they had 3 calibrators, Milky Way and LMC and 4258. And we have 3 here. They had Cepheids, and we have JAGB and TRGB. So there are differences here in calibration and where different kinds of systematic could arise. I'll point out that the largest systematic uncertainty we have is the distance to NGC 4258, which is 1.5%. We've compared both the Pantheon and the CSP samples, but just a couple words. This was a follow-up program that we designed to, after supernovae were discovered, we would follow them up with a range of wavelengths and get very good cadence, and also spec time coverage in the spectroscopy so that we get accurate K corrections. All of these data are used in the analysis input to our MCMC analysis, ultimately to determine the Hubble constant. And this was done in 2 stages. There was a CSP1 and a CSP2, and we tripled the sample going at the completion of CSP2. So here is our combined sample here. We're limiting the analysis to redshifts greater than 0.01, and they correctly pointed out by Bout et al. And Adam and others is that we really need to avoid the supernovae at low redshift. And we've done 2 different types of MC analysis, one using the common MC analysis and the other POC, and millions of different permutations and combinations of these parameters. We added in an extra parameter to allow for the dispersion in the calibrators. It's a small sample of calibrators at this time that it increases the uncertainty, and this will improve over time. So let me just say that in conclusion for today, that I think JWST is ushering in a new era of accuracy. It's similar to what HST did when it was launched 3 decades ago. And we now have distances from 2 methods, TRGB and JG methods, that are based on JWST data alone, and they're agreeing at the percent level in terms of offset. And that I think is important to say, that these are based on JWST data alone, and they can be applied in regions where the crowding, blending, and the extinction are very low. The distances based on Cepheids at this point are not based on JWST alone. We just don't have sufficient data to do that at this point. So we need to rely on optical data to correct for dust. And what we found in our blind analysis is when people use different period cutoffs, when they use different ways of defining the PL relation, when they use different ways of excluding stars from the PL relation, the outliers, they were getting different Hubble constant values, same data, same team, but different parts of the team. And that's a little disconcerting at the moment. That, again, will improve with future. So just say, I think more data at higher resolution are going to be required to measure the Hubble constant at 1% level from the Cepheids alone. The HST data are currently the limiting factor. But I'm optimistic. I think people ask, are we going to get to the bottom of this? And I think in the next few years, with increased amount of JWST data for more galaxies, we definitely need more galaxies now. The sample is too small with JWST alone, but this is we will get to the bottom of these uncertainties. So let me stop here, and I'm happy to answer any questions.
Thank you very much, Wendy. Very impressive work. Questions?
Thank you very much for a nice talk. Can you explain a little bit more about how you combine the different measurements, the TRGB and Cepheids and so on? Like, what you do if they don't match with each other? Do you have like some prior on them? How do you combine the error bars and this sort of thing?
Yeah, this is something that's still very much we're working on, and we're running many different combinations to try and come up with a robust value. We can give you a Hubble constant based on JGB and TRGB alone. We can combine them based on their relative errors. We can do a Bayesian analysis, which gives you more of the product of the various values and with their uncertainties, and they aren't much changed. But as I said, the Cepheids come in with a higher value. There is a discrepancy within our data set between the Cepheids and the JGB, TRGB stars. So I think this is something that we're going to have to take into account. There is a systematic offset, and that isn't so this is not, as I said earlier, a discrepancy with the high redshift universe. This is a discrepancy in the distances, and the scatter in the distances between the JGB and the TRGB stars is smaller than when you compare with the Cepheid. So the scatter does seem to be introduced by the Cepheid measurements, which is not surprising. There are more steps to it, and more crowding, more artificial star corrections, and as I mentioned, the colors still have a large scatter, so they're introducing uncertainty. So yeah, so we're creating a large table that shows the various combinations and permutations. But what I will say is we don't get values that are 73, 74, and there are ways to push the Cepheids higher if you make these are subtle differences, subtle choices that you might make, and where do you do a period cut? What outliers? It's which data set are you using? It's disconcerting at the moment. There are too many choices to be made with the Cepheids, and that's where we faltered in the blind analysis. Is completely blind, right? It's we're now comparing the photometry is calibrated, but different parts of the group were using, it turned out, different assumptions. This is what we would do to fit the PL relation, and you get a different H naught. So what I would say is we're getting a value of about 70, and it's hard to get a value that would be 73 or 74.
Hi, Wendy. Lloyd Knox here. And so you focused on ways to get ways to get distances to where you'd have host supernovae. And I'm wondering about your thoughts about the rest of it on the what's the state of the supernova side of things with and how differences in populations in the local supernovae and the Hubble flow supernovae can influence things.
Yeah, there are issues there too that I think we need to understand, and I think the first thing to be said is that the dispersion in the local sample is smaller than it is for the distant sample, and that's true in everybody's analysis right now. We don't quite understand the reason for that. The corrections, K corrections, and those sorts of things may be contributing uncertainties that we don't yet quantify or understand well for the distant supernovae. You would hope that the nearby sample would be well measured, you have higher signal to noise, and that the nearby sample is telling you something. This all again will improve when there are large samples that have been obtained in a homogeneous way, so that you can be comparing apples with apples. The nearby sample of supernovae is small right now, and there are 37 distances, and some of them are pretty crowded. They go out to beyond 40 megaparsecs, and maybe the photometry is good at 20 megaparsecs and still okay between 20 and 40, but beyond that, first of all, we don't know empirically whether those distances are well determined, and we'll see that as more galaxies get measured with JWST. But there's also the nearby ones in that intermediate region. They're brighter on average than the ones at greater distances. And even within, I think within the SHOES group, they've reanalyzed data between 2016 and 2022. It's hard to do photometry in these galaxies at an accurate level. And there is a systematic difference in the same data, same group between 2016 and 2022. So yeah, I think Rubin, as long as you can follow up with spectroscopy, the Pantheon sample now is based on 18 different surveys, and how you bring all those together. There are potential systematics that are locked in that. The CSP sample is done more homogeneously, but it's a smaller sample. So yeah, I think again at the 1% level. Now, we're not talking about solving the H naught discrepancy as a difference with the supernovae, but I think the SHOES team is finding that before the issues were more with the Cepheids, but now the supernovae, they've shifted relative to the Cepheid calibration, and there's still uncertainty, put it that way, that we can reduce in future, and that will happen.
Let's see, we have a question online, Adam.
Yes, Wendy, very nice talk. So my question is, so I looked closely at the talks you gave earlier this year after unblinding, and at that point you were showing all three methods, comparing distances. And at that point, the Cepheid distances you showed agreed very well with JAGB. the TRGB distances looked off by about 1/10 of a magnitude. Now you're saying that you're excluding the Cepheids. I guess my question is, aren't these choices something you have to commit to at the time that you unblind, since this a posteriori data selection can affect your H naught?
So, I think we hoped we were done at the time of unblinding. And as I said to you, so, there were two groups that ended up doing the Cepheid analysis, two groups that did TRGB, two groups that did JGB. So the Cepheids, the sample that we have now, I would say, is insufficient to determine this with the same level of accuracy as for the TRGB and the JGB. So, yes, if I was to say we did a completely blind analysis, we would have committed to the one way we did it at the time of unblinding. But these choices, as I said, I mean, as well as anybody, you have to allow for the fact that the sample depends on your period cut, depends on your outliers, and how you exclude stars, and how you're sampling within the period luminosity relation itself. And it was disconcerting to find that when you had two independent groups doing this, they came up with different answers. I find that very unsatisfying. And this will get better as we get more data, but it's where we are. So the JGB and TRGB analysis, JGB is completely blind, completely blind. The TRGB, as I showed you those bits to the tip, and that turned out to be, there was just a small displacement in the location of the ellipses. And as you can see, the fits are very good right now. That's just where they lie.
So, sorry, how come the shift in TRGB doesn't concern you post unblinding, but the new choices in Cepheids does?
No, it all goes into the uncertainties. That's reflected in our uncertainties have gone up as a result of this. And if we look at the tip of the red giant branch and sort of, stars that were fit, I would have preferred that at the time of unblinding that was better determined, but it wasn't. That's just, but if you look at the fits now, they're clearly good fits. And I think this well, Adam, there are some types of experiments that you can set up and do completely blind. And we did our best in terms of, all of the initial comparisons were done blind. I would not now characterize our study as a blind study. We can't, because we learned things after unblinding that
Sure.
Really have increased our uncertainties. And
can you just present like 70 variants of the analysis so that people can see? Okay, great.
So, working on it.
Okay.
So last question, we are really late now. Go ahead.
Yes, thank you. So your program had observed 10 galaxies. Why are there only 7 galaxies in the results?
Yeah, we've been analyzing the data and ascertaining where we get a very where we converge in terms of measurement of the JGB stars. And there are galaxies like the antenna galaxy that don't show as good convergence. So, again, in this table, we show what the value of the Hubble constant is when we include the galaxies that just have larger uncertainties. I mean, these are small variations here. By the time so this is the dm by dr here. By the time you get out to a place where you really are seeing convergence, and some of these others just have larger uncertainties. So we do the analysis with and without, but some are better measured. That's the answer to the question.
Great. Okay, we need to move on. Thanks very much, Wendy. This was very exciting. Let's get again.